Hello student, here is the question that a square loop carrying a steady current I is placed horizontal plane near to the straight line conductor. Steady state current is I by 2, or a distance of conductor, the distance from the conductor is shown in the figure, the loop will experience. So here you can see if current I by 2 is flowing in this loop, in this wire, that's the infinite wire which you have. So magnetic flux at this distance is R, and there will be some distance of, let's say that's equal to A, size of this square is A. Okay, so here magnetic field at this point, because it's perpendicular distance, magnetic field, that's B1 will be equal to mu naught into I upon 2 pi into R. Okay, on magnetic field at that point will be equal to, in this region will be equal to B2, let's say that's equal to mu naught into I upon 2 pi into R plus A. Okay, you can see magnetic field at B1 is greater than B2 because this value R plus A is more than R. Okay, so you can see over here that's the magnetic field is that's current is in this direction. Okay, so magnetic field will be inward. So here is magnetic field, this field will be inward, and this field will also be inward, and you can see that's current is inward, magnetic field is inward, and current is flowing like that. Okay, so force on that current carrying wire can be written as force due to current carrying wire can be written as I into L vector cross B vector, and the direction of L vector will be in the direction of current. Okay, so here is the current which you have, here is the current in this wire. Okay, for this wire the force will be, that's L vector, and B vector is inward, so force will be towards the infinite wire, so that's a force F1, let's say that's a force F1. Now look at this another wire, this wire current is flowing in like that, and this here is the magnetic field is also inward, so you will write that's the L vector and that's a B vector, so force will be downward. So you can see that's the force F2, so I am writing the force F1, so F1 will be equal to I into L, the wire of the length of the wire, let's say that's equal to L A, and that's B, value of B will be equal to mu naught into I upon 2 pi R. Okay, so F2, that's the force F2 can be written as that's I into that's current is I also flowing in that also, so that's I into A, size of that square is same, so that's equal to A, and mu naught into I upon 2 pi R plus A. Okay, so here you can clearly see that's value of F1 is more as compared to value of F2. Okay, so the net force on that net force will be because here will also be a force, so here is the F force, here is the same force F, because direction is current is like that, and magnetic field will be inward, so force will be on that will be F, and here is the force on that will be equal to same force. Okay, so but direction is this one upward. Okay, current direction is in this direction, and magnetic field is inward, so force will be but these two forces will cancel out on net force. Okay, because these two are equal forces. Okay, the net force on this loop will be equal to F1 plus F2 is equal to F1 vector plus F2 vector plus F3 vector plus F4 vector. Okay, so here you can see that's F3 and F4, these are 0. Okay, these will cancel out. Okay, now look at here, that force is F1, it in J cap, it's in J cap, and here is F2, that's in minus J cap, so F2 is minus J cap, so net force will be equal to F1 minus F2 in J cap direction, because F1 is greater than F2, because magnetic field B1 is greater than B2. Okay, so net force will be on this loop will be upward direction, so this loop will get attracted towards the wire. Okay, so a net attractive force towards the conductor. Okay, so that's correct, that will be a net attractive force towards the conductor. A net repulsive force, that's not correct. Torque, because torque, there is no torque. Okay, so because these all forces will pass through the center, so there will be no torque. Torque acting on the downward, no, that is option number first is the correct answer of this question. Okay, thank you.